Hello, everyone. My name is Yiran. I'm a PhD student from Rice University and MD Anderson Cancer Center. Today, I will present our paper, PET Hierarchical Feature Guided Conditional Diffusion for PET Image Reconstruction. So let's first start from introduce the imaging modality of positron emission tomography, the PET, and its imaging process. During the PET scan process, the patient is first injected with a small amount of radioactive tracer, and after it distributes in the body, the scanner detects the scanner to show the metabolic activity. We can see some example images here. So now let's see the imaging process of the PET imaging. During the forward imaging accretion process, the PET scanner here, which is actually the linear projection operator, detects and counts the photon coincident. The measured counts from different angles from the projections, which are then stacked the measured counts into the sinogram. The whole imaging process is based on a Poisson noise model. So what we are really interested here is the inverse problem, which is we want to recover the unknown tracer distribution, the PET image X, from these noisy sinograms Y. To solve the inverse problem, traditional methods like OSEM, MLEM always frame it as a regularized optimization problem. The data fidelity term ensures that the reconstructed image is consistent with the measured sinogram data. And due to the ill-posed nature of the inverse problem, we add a regularization term here to incorporate prior knowledge. However, we also need to rely on some assumptions when using such traditional methods for PET image reconstruction. For example, we need some accurate system geometry, we need point spread function, and we need to know the noise statistics, and we may also need to choose a suitable regularizer. These assumptions we may not hold in practice or in real clinical situation. So that's where the deep learning technique come in. We can think the deep learning method as a magic black box. So we just need to use a deep neural network. We can learn all of these components directly from the data. Like we can know the geometric relationships and statistical characteristics and appropriate regularization pairs by just using a deep learning model. And also we have greater flexibility and need fewer modeling assumptions. So recently there have been several deep learning based work that directly map sinograms to PET images. The deep PET is actually the first one to propose an end-to-end network for PET reconstruction using an autoencoder CNN. The deep PET is supervised by the mean square error loss. Such models, like the deep PET, that's solely supervised by the MIC loss, we usually call them regression-based deep learning models. So because of the nature of the MIC loss, they tend to average over the uncertainty, which means the reconstructed results from such models are always over smooth with suboptimal perceptual quality. So in order to improve the perceptual quality, some work start using advanced deep learning techniques, the generative models. One typical family of generative models is generative adversarial networks, the GANs. For example, in this slide, the DPLR-net introduces a GAN-based architecture with a Wasserstein loss to generate more realistic PET images. So although GAN-based method can produce realistic results, due to the underlying competitive nature between the generator and discriminator segments, they often suffer from unstable training process issue, which may introduce numerous artifacts and hallucinations in resultant images. So diffusion models are a recent breakthrough in generative modeling. They are very robust, scalable, and stable, and can generate highly realistic output through the denoising steps. So we adapted conditional diffusion model for PET image reconstruction by using sinogram as condition. In the forward process, we gradually add random noise to a clean PET image until it becomes nearly pure noise. This process is mathematical fixed and does not involve any learning. It simply defines how data is corrupted step by step. And the learning-based reverse process is the generative part. The model learns how to start from the noise and iteratively remove it given the sinogram data until it reconstructs a realistic PET image. So by simply using a conditional diffusion model, we call the CDPM, we can generate highly realistic PET images. But we also observe some issues about the performance of CDPMs. We found that it is not easy to maintain correspondence and consistency between the input and output images when they're from different domains. And it is difficult in capturing high-frequency details. And we also notice CDPM has slow convergence and low training efficiency. So to address these issues, we propose LogoPET. It improves the conditional diffusion model performance with a hierarchical feature guidance module. So specifically, our LogoPET has two parts. The first part is PNPNet, which generates hierarchical feature maps from mappings between the sinograms and PET images. And the second part is a CDPM, which is a standard 2D sinogram condition diffusion model using these features to guide final PET image generation. So we explain the PNP part first, which takes sinogram as input and output and overthrows PET images. We utilize a convolutional unit, which is the same architecture as commonly used the unit backbone in diffusion model, which consists of several ResNet and self-attention blocks. During the training, the PNP net is supervised by an MSE loss and the discrete wavelet transform loss. And this design ensures that PNP net can capture the useful representations that are both robust and structurally meaningful from input sinogram data. So once we get the learned PNP net, we input the sinogram and we extract the two lists of hierarchical feature maps from the latent space of the learned PNP net, the BD from downsampling blocks and BM from the middle blocks. So BD includes high-frequency information from the sinogram, which corresponds to fine anatomical details in the PET images. And BM includes compact, semantically rich, low-frequency representation that can guide accurate reconstruction in the decoder. And then we connect the learned PNP net to CDPM by incorporating these learned features as extra biases to the encoder and the middle blocks of this denoising network of CDPM. So this integration allows the CDPM to leverage the low and high frequency information from the learned PNP net. During each iteration of training, we randomly select a batch of sinogram and PET pairs and train by minimizing the denoising loss. And we also use the classifier-free diffusion guidance training strategy, which helps ensure the reconstructed results are more aligned with the conditioning information. So now let's go to the experiment section. We first prepare our data set. We simulate 2D FDG PET images using 20 3D brain phantoms from BrainWipe. And for each phantom, we extracted 55 non-continuous actual slices and generated their corresponding high-count sinograms. And we augment the dataset by rotate each phantom 5 times. And we use 85 brain phantoms for training, 5 brain phantoms for validation, and 10 brain phantoms for testing. We implement all our experiments in PyTorch on NVIDIA A100 GPU, and we perform qualitative evaluation in terms of visual inspection, and we use quantitative evaluation, use PSNR and SSIM. We choose 4 baselines to compare with our LogoPET. DuPET we have introduced before, which is a simple CN autoencoder, and CGAN, which is a standard conditional GAN, and peaks to peaks, which is a conditional least square GANs. and CDPM is a standard sinogram conditional diffusion model. We use the public configuration for all baseline models and train them until full convergence. We show our visual results here with 2 example slices with set-by-set comparison with the 4 baselines. The first column shows the input sinogram, and the second column shows the reference images reconstructed by the OSEM. And from the third to the 6th column, which correspond to the 4 baselines, and the final columns shows the reconstructed results using our proposed LogoPet method. So we can see that the LogoPet generates the most realistic reconstruction results among all methods. And CGAN Pix-to-Pix and CDPM introduce numerous artifacts, and the DeepPet produce blurry reconstruction with unrealistic fun details. So we summarize the quantitative results in this table. We can see that the LogoPet demonstrates a 0.59 dB improvement in PSNR compared with CDPM, and a substantial improvement of 5 dB and 3.7 dB when compared with CGAN and Pix-to-Pix. So we also conduct an ablation study to further show the effectiveness of our guidance in improving the performance of CDPM. We compare the LogoPet and the CDPM performance every 20 epochs in terms of PSNR and SSM over a total of 500 epochs. Here are our 2 key observations. The first is the LogoPet consistently outperforms CDPM in terms of PSNR and SSIM, which can see that the benefits of integrating our feature module. And the second one is the LogoPet shows strong performance even at early epochs, which means it has potential to improve the training efficiency. So in summary, in this work, we propose the LogoPet, which enables hyperceptual quality pet image reconstruction. And the experiment results show that our LogoPet outperforms several baseline algorithms in terms of visual inspection and PSNR SSIM. And the ablation study further validates the effectiveness of our feature-guided module. And our future work will focus on extend current methods and validate on patient data. Yeah, that's my presentation, so feel free to ask me any questions.